Welcome to already the last module of this MOOC on radionuclide production. In the first 3 modules, we learned about radionuclides, radionuclide generators, and how we can produce radionuclides. In this module, we'll discuss several often used separation strategies. From module 3, we know that when we want to produce radionuclides, we start by choosing and irradiating our target material. A small part of our target material then turns into the radionuclide we're interested in. And what we will learn now is how to selectively separate these product radionuclides from the target material. And after this, we can check the quality of our product. There are quite a few chemical separation techniques that we can choose from: precipitation, chromatography, solvent extraction, sublimation, and electrochemical separation. And today, we will focus on precipitation reactions. A precipitation reaction is defined as a chemical reaction between dissolved substances that form one or more solid products. They played an important role in the discovery of radium by Marie Curie, who used precipitation reactions to isolate radium from pitchblende ore in the late 1800s. And even now, precipitation reactions are often used, for instance, to recover target materials after irradiation. Using precipitation reactions to separate the product radionuclides from the target materials is a bit more tricky, since the actual concentration of the radionuclides is often very low. One solution here could be co-precipitation. Co-precipitation means adding a compound of identical or very similar properties to the solution containing the element you want to precipitate, for example, your radionuclide. By doing this, the effective concentration of the element increases, allowing it to precipitate. You can choose to either co-precipitate your radionuclide with an isotopic carrier, which has as downside that it decreases the specific activity, or with similar but different compounds. We can differentiate 3 different cases. When all compounds have dissolved, we talk about a solution. In a suspension, solid particles have formed, but they are dispersed throughout the solution. And when these solid particles have then settled and separated from the solution, we call it the precipitate, with the liquid above the precipitate called the supernatant. There are several commonly used methods to remove the precipitate from the supernatant. You could use a filter, which holds back the precipitate while allowing the supernatant to flow through, or you can use a centrifuge, which rotates the samples very rapidly, ensuring that the precipitate is collected in the bottom of the vial. Afterwards, you can pipette off the supernatant. You can get a bit of a feeling for whether or not a compound is likely to precipitate from the general trends in solubility. If your compound contains group 1 elements, ammonium ions, or chlorides, iodides, nitrates, or sulfates, it is likely to be soluble. On the other hand, if your compound contains oxides or hydroxides, sulfur, or if it's a carbonate or phosphate, then it's likely to be insoluble. These general trends will only give you an idea as to whether or not your compound might be soluble. If you want to know exactly to which extent your compound can dissolve, you need to look up its equilibrium constant. We talk about equilibrium when a saturated solution is in contact with a solid compound. Multiplying the concentrations of the 2 dissolved ions, each to the power of its stoichiometric coefficient, gives you the equilibrium constant. Let's look at an example. Say that you have a sodium chloride solution which you add to a vial containing 5.2 times 10 to the negative 6 molar silver nitrate. You looked up the solubility product of silver chloride, which is 1.6 times 10 to the negative 10, and you're wondering how much of the sodium chloride you need to add to your silver nitrate solution to form the silver chloride precipitate. The solubility product that was given equals the concentration of the silver ions times the concentration of the chloride ions. And since we know the concentration of silver ions, we can calculate the concentration of chloride ions by dividing the solubility product by the concentration of silver ions, which equals 3.1 times 10 to the negative 5 molar, which is telling you how much sodium chloride you would need to add here. In the next video, we'll focus on chromatography methods to separate radionuclides from their target materials, but first we'll practice with the concepts covered today.